Hi guys, so I was interrupted, but now we can finish that small unit about Archimedes principle, which is not that intuitive, and then we can move to Bernoulli principle, which is not intuitive either. Okay, I don't know what's going on here. Okay, so we talked last time about the situation when something is totally submerged, right? So in that case, when you have something in water, like we were talking about, like let's say you have a piece of rock that is being held by a string, it's going to displace its own volume in water, right? So the volume of the water displaced will be equal to the volume of the object because it's totally submerged. Now, the buoyant force is not equal to the weight of the object, you see, because the density of the object is larger than water. So you're going to have its weight here, and you still have the buoyant force here, but the buoyant force is smaller than the weight, so it wants to sink. And of course, if there is a string here, it's helping, balancing the weight. So all we can say is that the weight of the water displaced equals the buoyant force, right? Weight of displaced water. The other thing that we can say is that the volume of the water displaced equals to the volume of the totally submerged object. Submerged object. But as I've said just now, the weight is larger than the buoyant force. Now, if something floats because the density of that object is smaller than the density of the object, in that case, it's going to displace some water, but that water displaced will not be equals in volume of the whole object, right? So it's displacing some water, so I'm going to make that water that is displaced here. Okay, that's going to be a volume. Okay, maybe that volume. So that will be the volume of the water displaced. So maybe it's going to be like if you have the area A. So the area A here is a circle times that small h here. Okay, so that will be the volume of the water displaced. Now, it's not equal to the whole volume. The volume of the water displaced will be equals to the volume of the part of the object that is submerged. So it's not equal to the volume of the whole piece of wood, it's just equals to the volume of that little part here. Maybe I should do it, I insist, because once you understand the concept, then all the problems are easy, it's just algebra. Okay? So that part here, or the volume, that volume here of the object partially submerged, so only the part that is inside the water, if you find that volume here, then will be equals to the volume of the water displaced. So that part here will be equal to the volume here that I have in red. So the blue will be equals to the red. So in that case, when you have a floating object, something interesting happens. You see it's in equilibrium. So the weight of your object here will be equals to the buoyant force. Okay, so we have the buoyant force equals the weight of the object. So the main thing is that the object displaced is displacing its own weight in water. So it means if I measure the weight of that water displaced, it's going to be the same as the weight of the object. Okay, so each time something is floating like a boat, so let's say you have a huge cargo, like a huge boat here, it has to be really big. If this is 25 ton, okay, so this is your boat here, it's a big boat, the boat is 25 tons. What does it mean? It means that the water displaced, so you see it's displacing water here, that much of water has been displaced. Okay, you can imagine this is here. He's going to displace 25 tons of water. So it means if you are able to measure the weight of that water displaced, it's going to be equals to 25 tons. Okay, once you understand that, all those problems that are confusing is going to make sense. So the weight of that boat here is 25 tons. The buoyant force here is also 25 tons since it's in equilibrium, and that 25 tons is the weight of the water displaced, and that water displaced here, you see, is that volume here that is submerged. Okay, I think it's clear now. Of course, you're not going to find it here. If it's in the pool is going to rise. The water will rise like here. Okay, so this is very important to understand that each time something is floating, it's going to displace some water, but that water here has the same weight as the object because it's in equilibrium. Okay, and the volume of that water displaced will be not equal to the volume of the object, but only of the volume of the object inside the fluid. Okay, so again, in physics, the most important is to understand the concept. Once you understand the concept, then everything is easy. Okay, so let's finally, that's where I was last time. And I had to stop. So hopefully I can go here in do it, and then we're almost done with that part. Okay, so anyway, so this is floating, and the pan here is negligible weight, so it doesn't displace much water. We can forget about that. And then we put a piece of iron in it, and it's floating. It's floating because it's displacing enough water. So you see here that will be the water displaced, and the weight of the water displaced will be equals to the weight of the floating object. And the volume, that volume here will be only equals to the volume of the object that is inside the fluid. Okay, so what weight of water rises? So by definition, you see it has a weight here, and that will be the buoyant force. And we just say that the weight of the water displaced will be equals to the weight of the floating object. So we know that, and of course you have to pause the video. Am I recording? Yeah. So the weight of the object is 1 kilogram, and we're going to take G to be 10. Okay, we're going to say G equals 10 to make it easier. So that's going to be about 10 Newton. Okay. What is the volume of the water displaced? So it's displacing some volume, and I want to know what's the volume of the water displaced. But we know the weight of the water displaced, right? And remember that density equals mass divided by volume. So of course on the side, you know, when you are taking an exam, you can say, okay, mass equals rho. The mass equals density times volume. The volume equals the mass divided by the density. Okay, you are isolating the volume, so you cross multiply, divide. Okay, so the volume equals the mass divided by the density of the water. So this is density of water, the mass of the water, the volume of the water. So the volume of the water displaced will be 1. The density of water is 10. So that's going to be 10 to the negative 3 kilogram per cubic meters. So this is how much water it is being displaced, but it's also equal to the volume of the object inside the water. Okay, and that problem comes from Paul Hewitt, the Conceptual Physics book. Okay, so B, C. So now, again, like before, we totally submerge that piece of iron. Okay, so it's going to displace now its own volume, not its own weight in water, but you see, you can imagine that water has been displaced here. That water displaced will be equals to the volume of that iron piece. But now it's not floating, right? Because the buoyant force is going to be smaller than the weight. So you have the weight here, you have the buoyant force, which is smaller. And of course, here from the bottom, you're going to have the normal force, right? So you see that the buoyant force is smaller than the weight. That's why if you remove it from the pan, it's going to sink. The only reason it doesn't sink here is that it's displacing enough water to balance out the weight. Okay, so I don't know what the question is. Okay, so the volume in that case, because it's totally submerged, the volume of the water displaced, those problems are very good because they emphasize the concept. Okay, so the volume of the water displaced, it's going to be equals to the volume of the iron can. Okay, and what do we, how can we find the volume of the can, of the iron piece? We use that equation again, volume. So here we're talking about the iron, the volume of the iron equals the mass of the iron divided by the density of the iron, right? So here we have 1. The density of the iron is 7. Okay, that's the density of iron, 7,800. So 1 over 7,800, so 10 to the negative 4 meter cube. So what do we see here? That the pan here is displacing more water than if you just have a piece of iron inside. You see, it's like almost it's a factor of 10. Okay, so that means the pan, the aluminum pan, the pan displaces 10 times more water than the piece of iron alone. And because it's displacing 10 times more water, then that's enough to balance out the weight. And again, you remember we talked about that. If you have like a container, you take a piece of aluminum, you make it like a ball, it's going to sink, yeah? You make it as a ball. You can do that with Play-Doh. If you have your sister, little nephew, you know, your kids, you know, you can do that. You create a piece of Play-Doh. Oh, look, it's sinking. Okay, but ask them to make a boat, like something like that, in the shape of a boat. You're going to see it's going to float, right? Because it's displacing more water. So it's not that obvious. It's not that intuitive, okay? Okay, so that's good. So you see here, it's the same thing. Buoyant force here is exactly equals to the weight of the floating object, and that weight here equals to the weight of the displaced water. The displaced water will be that much volume. Okay, so it's not the whole volume, only that much volume. So part of the object is above the surface, part of it is below the surface, and it's floating. Okay, so only that part here, only that volume here will be equals to, I insist because those questions can be very tricky and confusing. See, it's only displacing that much water. So that will be your water displaced. It's not going to be here, it's going to rise. The water is has, I mean, from where it was before, let's say it was here, it went up, right? But anyway, the weight of the water displaced here will be equals to the weight of your load. Okay? Okay, so you can answer your question here. I think this is an easy question. I don't know how to go back. So if it's submerged, the buoyant force is the greatest. You can pause the video. If the masses are the same, it's going to be the greatest, of course, for the greatest volume. And the greatest volume, if the mass is the same, will be for the smaller density. Okay, if you have a small density, it's going to take more volume for the same mass. In that case, it's going to be the aluminium. Okay, density is mass divided by volume. So if you have a smaller density, you need to have a bigger volume. It's the story of the king, the crown of the king. So a fish has air bladder, so it takes air inside or outside. So if it increases the size of its bladder, it's increasing, it decreases the density, so it's going to go up. Okay, so you can read that slide. Okay, so this is a very cool example. I don't know what is in textbook 13.7. You can look at it. Kirk wheel. It's an amazing design in engineering. It's in Scotland. So you have some kind, it looks like a scale, okay? So you have, it's like you have two plates. That will be your scale here. And no matter the size of the boat, no matter the mass of the boat, it will be always in equilibrium. And because it's always in equilibrium, it doesn't take much effort to take that boat here and to bring it here. So you have water at two different levels. So here you have a lake, here you have a canal. So let's say a boat wants to go up. So it will go inside here, and this is always full of water. It's like a big pool. You just have to push a little bit on the other side and it's going to go up here. Okay, so you can learn about that, but it's the same. The idea is that the water always displaces its own, the object floating always displays its own weight in water. Okay, so if you want to, you can read here. I think there is a video to show you how it works. So you see here you have some kind of a lake, I don't know, connected to a canal, and here you have another canal. So it's touristic also, so people will get in those boats here. So there is a boat here, and you just need to give a little push here, and it's going to go up, and the boat can leave. So watch carefully. Boom, you see what happened? So this boat is going to go in, this boat is leaving, and this one is going to go down, and this one is going to go up. Okay, let's watch that again, because the video is very, see, this one go down, it's going to leave, and this one is going to go in this direction. And it doesn't take much effort. It's very easy to operate. So you see here, it's like a balance on both sides, and it's always balanced, given that it's full with water. Okay, so I will explain why. I hope I have the video. So this comes also from that drawing comes from Hewitt, from the book. And so what's happening, it's like you have a scale, it's like a balance, right? It's in equilibrium. On both sides you have a pool. Let's say the pool is empty, like a huge pool, a huge container. Fill up to the top, fill with water. And this is 300 tons, and this is 300 tons. And let's say there is no boat, so of course, you know, all it takes, if there is no boat, you give a little push and it's going to rotate up, and this one is going to rotate down. So you have to push it, but not that much, right? Because it's in balance. Now what's going to happen if you put a boat? So if you put a boat inside, so let's see here, you have 50-ton boat. Put your boat here. So the boat is 50 tons, but because it's floating, it's going to displace, so you're going to have water, overflowing here. And how much water is going to overflow? Exactly 50 tons. Okay, because you remember, if it's floating, it's going to displace its own weight in water. So even though I moved out 50 tons, I replaced it by the whole 50 tons, so nothing has changed. Now, if I put a small boat here, and the small boat is 50 tons, I'm going to remove that much water here. That little much of water is going to spill, it's going to overflow, and it's exactly 50 tons. So no matter how heavy the boat is that gets inside that wheel, or that container here, I always have 300 tons on that side, 300 tons on that side. Okay, because the main thing to understand is that something that float displaced its own weight in water. So it means that part here that is submerged, only the part that is submerged, right? Only that part that is submerged will be exactly the weight of the whole boat. Okay, but only the part that is submerged. So here I have a smaller part that is submerged because it's not as heavy, so it does not need to displace as much water, but that part here will be in water weight, exactly the weight of the load. Okay, isn't that interesting? It's quite amazing. It's quite interesting. Okay, let's do something that we have to memorize. So remember, we memorized already one equation with the ratio. The Beyond force equals the weight of the object times the ratio between the two densities. So we did that last time. Okay, the Beyond force equals the weight of the object. When something is totally submerged, the Beyond force equals to the weight of the object times the ratio between the density of the object divided by the density of the water. Okay, but now we have another equation to memorize if something is floating, so partially submerged, right? So let's see what's going on here. Okay, let's start again. What do they want? Okay, I want everything here. So that example comes from the book from Cutnell and Johnson that I have recommended, College Physics. It's one of these slides come from that book. So anyway, the thing that is not given here is that the density of pine wood is about equals to 550 kilogram per cubic meter. And of course, you know that the density of water is 1000 kilogram per cubic meter. So first thing, you compare the density, and of course that density is smaller than that density, so you can answer the first question. It's floating. Okay, we did that work before. And then what does it say? How much of the raft of the platform is beneath the surface? So you know that the total height here, is 0.3 meters, and that little here, that part of the platform is small h. We want to know how much of it is underneath the water. So it's a typical question because now we want to have an equation between the total height of the platform and the small height here, which is underneath the water. Okay, so we want the ratio between that small height divided by that big height. Okay, so it's floating. So what do we know? We know that the buoyant force equals the weight of the water displaced. By definition, that will be only true, but because it's floating, we also know that the buoyant force is also equals to the weight of the platform. So let's write that equality, the weight of the water displaced. And remember, density is mass divided by volume. So the volume equals mass divided by the density. Okay, so the weight of the volume displaced, it's going to be equals, and mass equals density times volume. So the weight of the water displaced, it's going to be m, the mass of the water displaced, times g, but that's going to be equals to mass is density of the water times the volume of the water displaced, which is not equals to the volume of the platform, because only that part of the platform is underneath the water, right? So that will be the water displaced, and the volume of the water displaced is only this part here that is underneath the water, times g. That should be equals to the weight of the platform. So that will be the mass of the platform times g, and the mass is density of the wood, and that will be the volume of your load, okay, of the platform times g. So I can cross that out. So that will get us to the equation that is worth memorizing. So the water displaced has a volume equals to the volume of the object submerged. So you can pause the video. Well, that volume, it's going to be the area. Okay, it's that part here is just like a small prism, like small here with that little h here, and that area here is just 4 times 4. So width times length times height. So it's going to be the small h times the area, 4 times 4, equals the density of your wood. Now the volume, in that case, it's the whole volume. So it's going to be the area times h. H is this, okay? This is h. So it's the height, the total height here. And this is the small h, okay? So you see, you can cross this out. And we get to the equation that I want you to memorize. I mean, I don't want you, it's up to you, of course. But we get to the equation that, okay, so this is algebra, but of course you can do the math first, and then you can reflect on it. I like algebra, so I'm going to do the algebraic expression. you're going to see that the small h, but you can do the math here. At that point, you can do the math. Okay, you can say, okay, this is 10 to the third. That's your unknown, equals density of wood is 550 times h. Okay, so you can already do your math and then you can generalize. Maybe it's easier for you if you do that. So here I have 0.3. Okay, so I'm going to do it this way because I think maybe it's easier for you to plug in first. So you see that small h equals 550 divided by 10 to the third, and here I have a 0.3. Okay, so you find that it's going to be 0.165 meters. But I want to look at that equation here, what it means. You see, you still have a ratio between the density, but here you have a height. Before we had the force, right? So the small h divided by the big H, so H divided by 0.3 equals the ratio between the density of wood divided by the density of the water. So that's the equation to memorize. The equation to memorize is that when something is floating, the height underneath the water divided by the total height equals to the density of the floating object divided by the density of water. Okay, so that's going to be very useful. Okay, so let's do that ratio in that case. So the small h divided by the big H, it's going to be 550 divided by 1000. So you get 55%, right? 0.55. So that part here, it's going to be 55%. 55%. So it's almost half. Okay, so that way you can do all kind of computation. So for example, let's apply our equation that we just found. Okay, let's see an iceberg. You have an iceberg, you see that we only see the tip of the iceberg, right? So that part here is submerged. I'm going to call that small h, and that part here is out of the water. And that's just going to be an estimation because, of course, you know, the volume here is weird. So we will have to find, like, estimate the volume out and the volume submerged, but about, okay, it's going to give us an idea. So we have that the height, we have that equation here equals floating object divided by the density of the water. But the density of ice is about, you know that ice float, right? So it's about 86% of the density of the water. So that's a fact. And that will be the density of water. So you can cross out, and what you get? 86%. So 86% of an iceberg, let's say 90% of an iceberg is below the surface. So therefore, you have something called the Titanic, right? Because he didn't see that part. So I guess they didn't take the unit about fluids, you know. So only 10%. So this is 10% of the iceberg, and this is 90% of the iceberg. Okay, so beware of iceberg. Okay, so that's also interesting. Density of whatever it's floating on, the boat is floating on, matters. So you all know that the density of salt water is larger than the density of fresh water. So it means you have to be careful that if something floats in fresh water, you have to be very careful when it gets if something floats in salt, like the ocean, in the ocean, right? Let's say you put so much load in your boat. So this is your boat here, and you have a lot of stuff here, so you barely float, right? But you are floating, okay, because the density of seawater is large. But what's going to happen when you go from the ocean, let's say you go to fresh water, because the density gets smaller, it's going to sink more, okay? You have to displace more water, and you can just sink. Right? It happened in, you have to look it up, in Quebec. In Quebec, you have a river called the Saint Laurent, and the boat, they come from the Atlantic, and they move to the Saint Laurent. And if their boat is too much loaded, it happened once. When they got to it happened to one ship. When it got to the Saint Laurent, it sank. It sank. And you all know, by the way, there is this what it's called, the Dead Sea. Okay, so you all know the story with the Dead Sea. People float. You cannot sink. You cannot sink in the Dead Sea. Okay, it's a very cool experience, but you have to be very cool that if you go to the Dead Sea, you should not have any cut, because that really hurts. But you see, you cannot sink. It's impossible for you to sink, because your body is made mostly of water, and this is salty. Okay, you will always float. It's impossible to sink. Okay, you can sink in real water, of course, and but in the Dead Sea you can't. Like you can do like lay and read your newspaper. There is no way you can sink, and the water is very good, like to cure like skin disease, so it's very famous for that. Unfortunately, they have environmental issues, so it's the level is going down. I think in Jordan they take too much water, so I don't know really the story, but it's really cool. Okay, and there was the story happened in New York, like okay, I should find the article, but there was a bunch of kids. It was upstate New York. I forgot exactly, but it was in the news. And okay, the kids were hiking, and you had a fall. In upstate New York, you have a lot of fall. The water is falling here, and here there was a pool of water here, and it was very bubbly. It's a lot of bubble. And the kids, they were from a swimming team, right? So they thought it will be cool to jump. So they jump in the water. So one guy jumped, and even though he was a very good swimmer, he sank. He died. He was drowning, and he was not able to go back to the surface. So his friends tried to save him, and they also died. So you can ask yourself what happened. What happened is that because the water was so bubbly, that the density of the water becomes so small that it was impossible to float, because your body is mainly water, and this is mainly air here inside the water. So it was like a pool of air, because you had a lot of bubbles here. So they all think it was a terrible story. It was kids, college kids going for a trip, and I could find the article for next time. So density matters. So if it's salt, you're gonna float. If it's a lot of bubbles, you will sink, and no one can save you, unless someone take you out. Okay, so that's for the story. Okay, so here is a nice application when you have a car battery and the density will change with the acidity. So it means when it's very acid, so it means when your battery is full, so you have a lot of acidic fluid, then that little bead here is going to float. So when you put your eye here, you're going to see green. But when the acidity gets less dense, like the bubbly water, for example, that thing is going to sink and you don't see it anymore. So you don't see green, but you're going to see black. So that means your car battery is discharged. Okay. You can also explain how balloon here float. So the most efficient, of course, if you use helium, and they used to do that, it's called blinds. You know those huge balloon, Heidenberg. Remember the story about the Heidenberg in Germany? So in New Jersey it happened. So it was filled with helium, and it was very good to float, so they could carry more weight here with a lot of people inside, because the density of helium is so small compared to the density of air. The buoyant force, is going to be larger, and because the buoyant force is larger, it's going to be easy to balance out the weight, right? So the buoyant force here will be equals to the weight of the water displaced. Now, because it was very flammable, they stopped using helium. No, it was not filled with helium. Sorry, it was filled with hydrogen gas, and it's hydrogen which is very inflammable, and that's why it caught fire. So now the balloon that float, they are filled with helium, still a smaller density than air, but it's not as good as hydrogen. Or you can also have some hot air. So if you have hot air inside here, hot air. So remember, air is like the ocean. Okay, it's like you have something submerged in the ocean. So except it's an ocean of air. So air is still a fluid, right? And in that case, you are totally submerging. So it's not floating. Okay, we are back to the situation where it's totally submerged, right? So totally submerged. So it's going to displace its own volume in air, but air which is cold, right? And if you displace enough cold air, so the volume displaced has to be very big, so that's why those balloons have to be really big, then you can have enough buoyant force that you can rise. For example, you can go up in the air, or you can just stay in equilibrium. So by the way, you know the balloon that you buy, the helium balloon that you buy, and then you let go, they're gonna rise. But at some point, because the density of air gets smaller and smaller, at some point it cannot go higher, right? So at some point the buoyant force will not be hard enough, big enough to bring it up higher, and the pressure is smaller. So because the pressure is smaller, because you have thin air, your helium balloon is going to burst and it's going to fall back on Earth. So that was it was back to the situation when something is totally submerged and the buoyant force will be equals to the weight of its own volume in air. So it's not partially submerged, right? So do you have a buoyant force? Yes, we do, except that because our weight is so big, it's not going to do anything to us, right? almost done. One challenge problem and then we good. Okay, so we are in the ocean. We are on Earth. The Earth has an atmosphere. The atmosphere is very thin. It's like an orange skin relative to the whole orange. So anyway, we're in the ocean here. And of course, we're going to have a buoyant force. But the buoyant force is much, much smaller than our weight. And of course, you have also normal force here balancing out the weight. Okay, so you're not feeling the buoyant force. It's not that it's not there, it's just that you don't feel it. So here's the challenge problem. You have a boat and you keep adding people. The boat has a mass of 120 kilo when it's empty and it's 3 meters long. Okay, so that will give you the area, 1 meter wide and 0.24 deep. So you have the volume. Okay, so that you have the age here, total age. How many 85 kilogram people could fit in that boat? Okay, so you can pause the video and try to do this one. It's worth it to try to do it. So it's a floating problem. So if it floats, then you have the total weight, and the total weight is the weight of all the people plus the weight of the boat. So the idea is that to find the total weight. If I have the total weight, then I can remove the weight of the boat and divide by 85 to see how many people it can fit. Then if it's floating, it will be in equilibrium with the buoyant force, right? Okay, you have different way to do it. So try to do it. So we need to find, so we can say that the buoyant force equals the weight, the total weight, right? And the total weight, you know that it will be the 120. We're going to find that total weight. We want to find the total weight, okay? So what's the buoyant force? It's going to be the weight of the water displaced. You see, it's displacing water, and here it's about to sink. So the weight of the water displaced is going to be the density of water times the area. The area is given times how much is underneath the water, right? How much is underneath the water? I don't know, because it depends how many people are inside. More people you know, you go more submerged the boat will be. Okay, it's going to be the total weight. Okay, so here I'm going to have 1,000 times the area is going to be 3 times 1. And here the height, it depends how many people. But at worst, the thing that, like when it's about to sink, it means it's totally submerged. So I'm going to do the worst. Okay, so that happens when it's about to sink. So that's going to be 3,000. It's going to be, I didn't do the math, 3,000 times 0.24. Okay, weight. So I put a G here. So weight times G is going to be the total mass times G. So I'm going to find things in kilogram, right? So that's going to be how much I have here, that's going to be, so that cross out, that's going to be 720 kilogram. So that's worse, okay? You don't want that to happen. That 20 kilogram, it's going to be the mass of the boat plus the mass of the main. So the mass of the main is going to be 600 kilogram. So 600 kilogram divided by one main, so 85, it's going to be 7. So with 7 main, you're going to sink. You're sinking. So so you want the only way it float, like it's really about to sink, it's going to be 6 main. So that will be the answer. So, okay, so next part, I will go into Bernoulli. Bernoulli, that will be our last video. Hopefully I can do it.